Hello, so we're going to solve another problem pertaining to groups. So we'll just call it problem 1. And what I'd advise you to do is to try and solve it on your own first and then check the solution, the explanation later. So let's call G a group. Oh, we don't know it's a group yet. That's what we're trying to prove. So let G be any set. So I would say it consists of elements of the form a plus b root 5, where a and b are rational numbers, right? And so our job is really, we want to prove that all non-zero, we want to prove that all non-zero elements of G form a group. That's our task, right? In other words, we want to show that G without 0 is a group, right? Alright, so let's work this out. Let's actually work out a proof of this principle. Well, firstly, we don't want to keep saying G without 0, so let's rename it. Let's rename it H. Let's say H. Set H equals to G without 0. Right, that way we can, our problem transfers from proving that G without 0 is a group, it transfers from that to just proving whether H is a group, right? And how do you prove that something is a group? Well, if you want to prove that a set is a group, you must show that it satisfies 4 properties. Right, so the first property it must satisfy, as we saw, is closure. The set must be closed under the operation, and here we're talking under multiplication, by the way. Right, I forgot that. We want to prove that H is a group under multiplication. Alright, so the set is closed. The other thing, we need to prove that there exists an identity element. The other thing we want to prove is that an inverse exists. Right? Every element has an inverse. We also want to prove that associativity holds. Associativity holds. If our set G satisfies all 4 properties, then H really is a group. Right? In order to establish these properties, we are going to be depending a lot on the real numbers. So let's first establish something about the reals. Well, consider the set of real numbers without 0. My claim is that under multiplication, these things actually form a group. Right, well, let's check that out. Closure, kind of straightforward. If you get one real number a and multiply it by a real number b, your answer is going to be a real number. So, right, your answer is going to be some real number. So it is indeed true that the set of real numbers without 0 is closed under multiplication. Identity, well, yes, there is an identity, namely 1, right? A times 1 equals to a for any real number a. How about the inverse? Well, if you have a non-zero element, then its inverse is just 1 over a, so the outcome still gives us 1. So that's pretty clear, right? And associativity holds as well. Is if you have a, b, and c, well, you could multiply a times b first, then multiply a result by c, or multiply b and c first, then multiply a result by a. So associativity holds as well. What this tells us is that R without 0 is indeed a group under multiplication. Right? Why is this important? It's because we're going to inherit a lot of the properties of R in order to help us prove things for our set H. Right? So we're going to go ticking off things on this list, and if we tick off everything, it would mean that H satisfies all these properties. So let's start with things that are easy to show. For example, associativity doesn't seem like a big deal because we realize that all elements of H are of the form a plus b root 5. Right? That's important to note. Well, a is a rational number, b is a rational number, and root 5 is a real number. So this entire thing is a real number. That means that if you get any, if let's say if you get any three of these, any three elements of H, and you multiply them, you're multiplying real numbers. And we know that associativity holds in the real numbers, right? And so because it holds in the real numbers, it must also hold in H, right? So maybe to put it a little bit in words, is if you have R, S, T elements of H, we know that R is real and S is real and T is real. And so RST, this product must satisfy associativity, right? Because if it didn't, then it would mean that the reals do not satisfy associativity, right? So we've ticked that off the list. Associativity holds. The other thing that might be easy for us to show is identity, right? Once again, if you pick any element of H, like for example this one, well, we notice that the element is a real number, and we know that any real number times 1 gives you that number back. So any R element of H, which is a real number, when multiplied by the number 1 gives me R, right? So we could immediately claim that 1 is the identity element for H, but we need to be a little careful. Why? Because the identity element must also be an element of H. That is, we do not know whether 1 is an element of H or not, right? We need to prove that 1 is an element of H. Well, how do we prove that? We notice that 1 equals to 1 plus 0 times root 5. 1 is a rational, 0 is a rational, and root 5. So the element 1 satisfies the form that an element has to have in order to belong to H. And so 1 is an element of H, right? And so it is indeed the identity element for H. So we've proved that an identity exists. Our major task is to prove inverse, right? Another thing we're going to try and prove is the inverse. Every element must have an inverse, right? Inverse just means, like, for any R element of big H, our set, we need to find some element R inverse. R inverse must also be an element of H, such that R times R inverse does indeed give us the identity. In this case, the identity is 1, right? So let's pick an arbitrary element of H. Let A plus B root 5 be an arbitrarily chosen element of H. If it's an element of H, it can't be 0, and this is particularly important, right? So we're going to guess what the inverse is. It's going to be what you'd hope it is. That is, the inverse of A plus B root 5, we're going to set it to be 1 over A plus B root 5, right? Obviously, this gives us 1 as an outcome. But again, as we saw here, the inverse must be an element of the set itself. So a natural question to ask is this beast over here really an element of H? Right? What we're claiming to be the inverse. Well, we can see that it is, and the reason is 1 over A plus B root 5, right, is really the same as 1 over A plus B root 5 multiplied by A minus B root 5 and A minus B root 5 once again, right? The outcome really is A minus B root 5, right? And here we just do the difference of two squares, 5b squared. The outcome now becomes A over A squared minus 5b squared plus negative B over A squared minus 5b squared times root 5. Right? Well, notice the form of this. All these elements A and B are all rational numbers. So this entire thing here is a rational number. We also know that this is also a rational number, right? And so this element, 1 over A plus B root 5, the inverse of A plus B root 5, the proposed inverse, we don't know yet, is of the correct form for an element to belong to H. Our only question has to be, can this element be 0? Well, obviously it cannot, because we chose A plus B root 5 as an element of H, and if it's an element of H, it's non-zero. So if you divide 1 by something that's not 0, there's no way you can end up with the entire thing being equal to 0. That doesn't make sense, right? And so we see that every element, right? Every element of H has an inverse, and that inverse is an element of H as well, right? And so we've now proved that every element has an inverse. Our main task now remains to prove closure, right? How do you prove closure? Right? That's our main challenge here, to prove closure. Well, what does closure mean again? It says if I pick R and S, if R and S are elements of H, then it must be true that R times H is also an element of H, right? For any R and S, right? That's what we're trying to prove. So let's actually show this, right? Let a plus b root 5 be an arbitrarily picked element of H, and let c plus d root 5 be another arbitrarily picked element of H. Our task is to prove, right, that a plus b root 5 times c plus d root 5 is actually an element of H. That's what we're trying to show, right? Well, let's actually expand this thing, right? So if we expand this, we have AC plus AD root 5 plus BC root 5 plus BD root 5, right? I want to make sure I didn't make any errors because my algebra is questionable, right? So BC root 5, BD root, oh, this is BD times 5, right? So I was right to check this after all, right? So I could write this as just 5BD. So alright, so 5BD. Right? I think I have everything in shape there. So let's collect like terms here. So now we have AC plus 5BD plus AD plus BC. All of this multiplied by root 5, right? Our claim is that this must be an element of H. Well, we know that A and B are rational numbers because they're elements of H. C and D are rational numbers too. And so we know that whatever this is a rational number, and whatever this is also a rational number. Our only question is this. So this thing is of the right form. This beast here is of the right form to be an element of H. Our main source of concern is we do not know whether this thing equals to 0 or not, right? We do not know that. So of course, if it's equal to 0, then we have a problem, because that means this is not an element of H, and so H can't be a group, right? But if it isn't, well, then for sure, right? That would mean that this is an element of H and would have proved that H is closed. So let's suppose, for the sake of contradiction, that this beast actually equals to 0. Right? If that equals to 0, then what we are really saying is that AC plus 5BD equals to 0, and we're also saying that AD plus BC equals to 0 as well. This thing equals to 0 and that thing equals to 0. Because if one of them is non-zero, then right, it's not gonna work out. So, well, let me call this equation 1. I'm gonna call this equation 2, right? And let's do a little gymnastics here. Let's see. So let's see what we can conclude from let's say from 2, for example. Let's start from 2, right? Equation 2 tells us that I'm going to solve for A. A equals to minus BC over D. That's what A tells us. So if we plug this A back into 1, well, 1 now becomes wherever we see A, we are going to plug in minus BC over D. So we'd have minus BC over D times C plus 5BD equals to 0. And simplifying further, we now end up with minus bc over d minus bc squared equals to minus 5bd, which would then mean that minus bc squared equals to minus 5bd squared. Right? And so from here we can cancel the b's out and the negatives, so we really have that c squared equals to 5d squared. And in particular, this tells us that c over d equals to root 5, right? When you actually do the simplification. Well, c is a rational and d is a rational, so c over d is a rational. What this is telling us is that c over d is an irrational number, because we know that root 5 is irrational, right? So this is a contradiction really, that a rational number equals to an irrational number, right? And so our assumption that this element that we created after multiplying equals to 0 cannot be true. But maybe you're doubting me a little bit. You're like, how do we know that root 5 is irrational, right? Because that was not like proved anywhere or anything. So maybe to see why that's true is c over d equals to root 5 can be written as c equals to d root 5, right? C equals to d root 5, right? So how do we simplify this better? Let's see. So actually, it's better if I write it like this. We're saying that c squared equals to 5d squared, right? So notice something here, like this is c squared and c is an integer, right? Or actually I can't think of a better simplification for this. So well, actually c is a rational and d is a rational, so that means that c can be written in the form p over q, right? So c is of the form p over q squared and d is of the form r over s squared, say. So let's say r over s squared, right? Let's write it like that. And squaring out, we now have p squared over q squared equals to 5r squared over s squared, right? And so we end up with p squared s squared equals to 5r squared q squared, right? And so the bottom line is, now we have some integer squared, right? So let's call this integer m or something, really doesn't matter, right? And let's call rq another integer. So what are we gonna call it? P. We already have p, so maybe n. Let's call it 5n squared, right? So we are claiming that this equation is true. But notice, and if you have an integer squared, right, we know that 5 is in the prime factorization of m squared. This is an integer. It's in the prime factorization of m squared. But since we have m squared, that means that every prime factor of m must be contained to an even power, right? So this 5 here must appear to an even power. But now notice, either 5 is in the prime factorization of n or it is not. If it is in the prime factorization of n, then when you square it, you're going to have the 5 here raised to an even power. Multiplied by 5, now you have 5 raised to an odd power, which is a contradiction because this m is a square, so 5 must appear to an even power, right? Suppose instead that n has no 5 in its prime factorization. Well, that means that the only 5 in 5n squared is 5, which is another contradiction because m squared implies that every prime factor must be raised to an even power. And so this means that this equation is actually nonsense, can never happen, right? And so we have a contradiction here, which means that one assumption we made must have been wrong, and the assumption we made was the wrong assumption was to claim that after multiplying two elements of h, your outcome is something that actually equals to 0. That doesn't happen. Never equal to 0. So you have an element that's of the form of elements of h and that's non-zero. Well, that element is an element of H. So what we've actually succeeded in showing is that you combine any two elements of H, and your result is also an element of H. Well, this means that H is closed, right? So we've shown that it's closed. H is closed, H has an identity, H has an inverse, H is associative, so H is a group, and we are done. So thanks for watching this video. Hope to see you on the next one.